Hey, how's it going? This is going to be a walkthrough of the AQA GCSE Computer Science Paper 1 Specimen paper. So this wasn't a real exam, this was just produced as an example of what an exam would look like. So there aren't any grade boundaries to compare your mark against, but my main recommendation is to do the paper before you watch this video. There are only finite papers available for you to practice. Don't waste it by watching this video first. Hopefully this video will be helpful afterwards, perhaps to show you how you could have got the marks. Or if you're revising the night before the exam, you want to see what a paper looks like. So the only real important information on the front page is that it's an hour and a half long, which is a pretty standard length for an exam at GCSE. You've got to do it in black ink, but that's the same for all papers, and in pencil only for drawing, although pencil is good for things like truth tables and algorithm questions. So you might want to do it in pencil first and then go over it in pen. And you can't use a calculator, that's important. You can't use a calculator, don't bring a calculator into the exam. The maths is really easy, it's not going to be very challenging at all, and it's worth 80 marks in total. So if you did a mark a minute, like most people advise, you have 10 minutes free at the end, but some questions are going to be harder than others. So if you find, let's say, the algorithm question is hardest, you might want to allocate 10-15 minutes on that question alone and make up the time in other areas of the exam. So you want to go in with some kind of technique or some tactic you've considered before you actually take the exam. And if you don't know already, there are a set of videos on my channel that cover the whole paper 1 playlist of theory, so make sure you go to the correct playlist. So AQA GCSE 9 to 1 Computer Science Paper 1, and the same for Paper 2 as well. So we start by looking at two programs that add together two numbers. One is written in high-level code and one is in low-level code, i.e. machine code in this case. And we've got to first of all show you two lozenges to give reasons why programs are most commonly written in high-level languages instead of low-level languages. So first of all, does it save a programmer time to write in high-level code? Well, it does, because this is much simpler than just a random binary. We have to look stuff up, we have to look up what this means in binary, but we know kind of implicitly what this means, so it does save the programmer a lot of time. So that's one of our two correct answers. The next one, programs will always run fast in high-level code. That's not true. They need to be translated to machine code. This is already in machine code. It can be executed directly by the processor. This has to go through the translation process, which takes time, and that means that it's going to be slower than low-level code. High-level language code is often easier for humans to understand. That's correct. That's I guess quite obvious. That's anyone could really understand what this means, whereas this is just doesn't mean anything, and so that means we've kind of used up the last two. Let's just disprove them to make sure we're correct. So they only understand high-level languages. That's not true. They don't really understand them at all. They have to be translated to understand them, in quotes. And the last one, the high-level programs are often easier for a computer to code. Well, I'm not really sure what they mean by that, but that's not true. It's going to be harder. They've got to kind of decompose this whole statement to match up to the binary equivalent. For part 2, as I say, the low-level program in figure 1 is in machine code, so just zeros and ones in binary, and we've got to suggest two reasons why it would have been better for the programmer to use assembly code instead of machine code. So low-level code is both machine code and assembly. So assembly is more kind of like add R1, so it's slightly more human readable, but still it's not ideal. It's not as good as high-level code, but there are loads of advantages of using assembly. So we're talking in terms of machine code versus assembly here. So assembly that's awful handwriting, but it's more readable than just which could be the same equivalent statement. So clearly that's more readable. So assembly is more readable than machine code. Kind of the whole point of assembly code is it uses mnemonics, which is a way of remembering things. I hope I spelled that right. So add is a mnemonic. Basically, the instruction bit of the assembly statement is a mnemonic, and so it's there to help you remember the statements. No one's really going to remember just the binary equivalent like this. You wouldn't remember this as add R1, but you would remember add R1. It's much more memorable. So these are two non-technical reasons, because really machine code is still going to be faster than assembly. Assembly is going to be translated using an assembler, but in terms of our ability to code, often assembly, well, in almost all cases, assembly is preferable. Figure 2 contains a subroutine that returns a value. I may have taught this as subprogram, same thing. It's a kind of out-of-line block of code that does a very specific purpose. So in this case, do something. I'm not sure what yet. We might find out in a couple of minutes. So we've got to first of all complete the trace table for this subroutine call when the parameters, or the arguments I should say, are 3 and 4. So A is 3 and B is 4. And okay, so we need to basically trace through ourselves and work out what happens at each point in the program. So first of all, we have our parameters going in, so A and B, and then we have C being equals to A and B. So let's first of all just write down what A and B are initially. So A is going to be 3 and B is going to be 4, and C is going to be a plus b in a kind of a first stage of a program, so c is going to be 3 plus 4, which is 7. The next part of the program is a while loop, so we're going to repeat this code embedded until a is greater than c. So at the moment a is less than c, 3 is less than 7, so we're going to loop. So a equals a plus 1, so the current value of a plus 1 is the new value of a, so a is 3, so it's going to be 4. Then b is the current value of b minus a, so the current value of b is 4, minus a is going to be 4 minus 4 is 0. And nothing happens to c at this kind of little location in the subroutine. People get a little bit hung up about where they leave gaps in trace tables. It actually doesn't really matter as long as it makes sense to you. Trace tables fundamentally are there for testing, really. So that's the first kind of iteration of that while loop, but a is still less than c, so we need to keep going because 4 is still less than 7. So a equals a plus 1, so 5 is now the value for a, and b is going to be b minus a, so 0 minus 5 is minus 5. A is still less than c, so we loop again, and this goes to 4, and minus 5 minus 4 is minus 9. 5 is still less than 7, so we loop again, so a becomes 5 plus 1, so 6, and b becomes minus 5 minus 6, which is minus 11. And still a is less than 7, nearly there though, so we loop another time, so this becomes 7, and minus 11 minus 7 is minus 18. Now crucially, a is not less than 7, so we don't loop. This is, it's got to be either side. This isn't less than or equal to, this has got to be completely less than 7, so it's got to be 6 or less. So we don't loop, we now kind of skip to this return statement, so we have to return b. And we don't really have to write that, we can just leave it as it is. Trace tables are really easy in practice, often worth a few marks, and you've got to be just very careful with how you trace through the program. Just take your time and you'll be fine. Don't worry too much about exactly where it's more the values in the columns which matters rather than kind of if you've left a gap or whatever. For part 2, we're told the program mistakenly tries to shorten the subroutine by replacing the lines where c is initialized to a plus b and the start of the while loop by kind of combining the two steps by replacing c with a plus b. So this is a mistake. This is what is known as a logical error because the code still works, just not as the programmer intended, because this isn't going to have the same effect as this. So we need to explain why that is. So if we go back to here, this is outside while loop. So c isn't affected by the while loop. Nothing happens inside the while loop to c. So c is a constant. C stays the same throughout the program. And we're basically comparing our sort of dynamic value that we're changing to this constant. Whereas if we replace c with a plus b changes every time the loop goes through. So we're changing what we're comparing it to. We're not comparing it against a constant anymore. So exam technique here, we've got 2 marks, so we kind of need to come up with 2 bullet points, and maybe you'd want to write it out, but I'm going to save time and do bullet points. So first of all, c is kept constant or is a constant, whereas a and b change. Or we could do a plus b change. And that's enough to get you the 2 marks. You don't really have to explain exactly why it affects the operation because we don't really know what the operation does yet, we haven't been told. We now need to work out what value is returned when we have x as an argument where x is just any positive integer. So we're looking at a very general case here and we're basically focusing on the effect of 0 if 0 is our b parameter. So we go back to our code to actually see what effect this has. So c is initialized to whatever a is, so any positive integer plus b. So c is the same as a if b is 0. Which is an issue because then we have to compare a to c, and so a is going to be the same as c, so a is not less than c, so this loop never gets called, and we just jump to the return statement for b. So b is 0, so that's why 0 gets released, it gets returned when 0 is the second parameter, so just 0 is our answer. Question 3 is about images in binary, so we're told that black pixels represented by 1 and 0 represent white pixels, and they're arranged in a 2D array. And this algorithm we've got here, the pseudocode, calculates the number of black images in a bitmap image and it stores it in the array called image, which has 4 rows and 3 columns. And 4 aspects of the code are missing. So first of all, we've got to write I've got to select which should represent L1 here. So number of black equals what? So the point of this whole algorithm is to count the number of black pixels, and it's going to have to start counting at 0, and this is going to be our kind of counter variable, the number of black pixels. And you can see here that it gets incremented 1 if it is black, basically. So that's fine. Now looking at what operator should be at point L2, whether it should be equals, greater than or equals, or less than or equals. For this perhaps we have to work out slightly more about what's going on. So we've got This is important here. The array indexing starts at 1, which often array indexing is 0 indexed, which is why they have to clarify that it does start at 1. Often, occasionally in pseudocode it will start with 1, like in this example. And so x is going to be our index for our rows, and then y is going to be our index for columns. So an array is stored as, or 2D array is stored with 2 indexes, so image is our, in fact it's written there. Anyway, so you would use 2 indexes. This would be the row, and this would be your column, if you imagined it as like a table. So we have a set number of rows and columns. We're told that there are 4 rows, so really we should have another one. So there are 4 rows, so 4 lots of x, or x at maximum should be 4, and y at maximum should be 3. So first of all, our first iteration of the x indexes, we have to say, well, x is less than or equal the number of rows, because we can't go out of bounds. If we put x as 5, this isn't valid because our array isn't that large. This would cause an error. So we have to make sure we're less than or equal to the number of rows. So this is going to give us our answer of less than or equal to. Looking at L3 then, so what value this is going to be, it's within the y index loop, and this is the general way you loop through 2D arrays. So first of all, you look at a single x, a single row index, and then you look at every column for that row and you iterate that through. So we're looking at whether the item at a specific point equals whatever this value is, then we're going to increase the number of black plus 1. So we're counting the number of black pixels. If it is this value, then it's going to do this. So it's going to be whatever value is for a black pixel, which is 1. So the value of L3 is going to be 1. So L4 is here. The whole point of the while loop is you're going to exit the while loop eventually. Otherwise, if you don't increment the value in the expression, you're going to have an infinite loop. So we need to increment y in order to move along our loop. Essentially, we don't want to get stuck repeating forever. So we need to increment y, and it's going to be very similar to here. We have to also increment x. We've got 2 loops nested, so we have to do y equals y plus 1. By the way, the arrow is just a way some people like to write their pseudocode to represent the initialization of variables. It means you don't have to worry too much about the comparison operator. Question 4 is very similar to the question we looked at before. At least initially, we've got to do a trace table for a binary search algorithm. So hopefully you know how this algorithm works. If not, I guess you don't necessarily need to yet. So we need to do a trace table for this algorithm, and again, the indexing starts at 1, so that seems to be AQA's kind of convention, and the line numbers don't count. Okay. By the way, when you have to put something in a table, I would recommend you do it in pencil first, just so you can afford to make a mistake and not have to, get other paper and have to do it yourself. So again, we kind of take it step by step. Let's do all the sort of initialization on the first line. So val is 43, left is 1, right is the length of the array, so 1, 2, 3, 4, 5, 6. The length being a function. And then personally I would go on to the next line, because that's sort of, in my head at least, this is sort of one construct when we have a while loop here. So what we're doing, we're going while left is not equal right. So we keep doing this until left equals right. We're initializing mid to left plus right div 2. So first of all, left plus right, so 1 plus 6 is 7, div 2. So div is integer division, so we're basically saying how many times does 2 go into 7, so how many full times does 2 go into 7, sorry. So 2 goes into 7 3 times, remainder 1, but we're not concerned about the remainder. The remainder is mod, I'm not worried about that. So this is going to be 7 div 2 is going to be 3. So that's the value for mid, again, because that's how many whole times 2 goes into 7. And then the next bit is if the value is less than or equal to array mid. So this is using the value of mid to index the array, so this is going to be the third item in the array. We're starting counting at 0, so this is going to be 13. In fact, I said I was going to do it on a separate line, so let's move that. So you can see we've got 2 conditions here. If val is less than or equal to this value here, so what is val? So val is 43 and it's clearly greater than 13, so therefore it's going to be the else that gets evaluated. So left equals mid plus 1. 3 plus 1 is 4, and this is finished executing then, so we can go back to the start of a while. So does left still not equal right? Yep, they're still different. 4 is different to 6, so we evaluate this again. So mid is then going to be 4 plus 6, 10 div 2, so 2 goes into 10 5 times and no remainder. And then using 5 as the index for the array, so 1, 2, 3, 4, 5 is now 6, 5, 5. Val is now less than this value, so we can do right equals mid, so right now becomes 5. We start the loop again because they're not equal still. 4 is different to 5, so mid is now going to be 9 div 2, which is going to be 4, and then the fourth index is 1, 2, 3, 4, so it's 43. And this condition is now true again because value equals, this is less than equals this value. 43 is the same as 43, so right equals mid, so this is going to be 4, and this is going to be our final truth table, because after this it will see that left is the same as right, so it kind of skips to the end. A bit of a messy trace table there. I'm not sure how well I did my gaps in between lines. I hope that made sense. But actually, as I said before, the actual gaps in the columns don't matter as long as the values are in this order. Basically, the examiner will look at the order of his values, so he or she will look at the fact that you've only got 43 here, this remains constant, and it's the order of his values that matters, not where you put the gaps, because it's a bit arbitrary where you sort of look, where a construct starts and ends. So I hope this is okay. For the trace table question, you don't need to know anything about binary search, but now it's testing you on your actual knowledge. So why would this array not work for this algorithm? Well, this array is not sorted. A binary search algorithm needs to be sorted, as does linear. Only binary search needs to be sorted. So this, you can see here, is sorted. It works okay. If you were to do this in practice, you'd have to use the sorting algorithm first on your list and then apply this algorithm. So this wouldn't work because it's unsorted. Just to remind you of how binary search works, if this is our list and we were to, assuming it's sorted of course, the binary search algorithm will divide it into, look at the middle item, and if that item is smaller than your target item, that means your target item must be in the top part of the list if it's ascending order sorted. So we can kind of get rid of this bit, then it will divide again and the same thing will happen. Is this item less than your item? If it is, it can get rid of this bit and it will keep going until it finds your item. So that's how it works. It needs it to be sorted for it to help, the whole premise, it needs to be sorted. Another multiple choice question then, and like most bits of code, there's always a replacement thing you could do that has the same function, but we're asked to state which one of these is not possible. You can't replace it with line 5, which is this comparison. So while left is not equals right, so is one of these not equivalent? So it's probably best to do just look through each of them. So while not left equals right is the same thing as saying not equal to, so that's obviously going to be fine. This one straight away jumps out and not being correct because you have an and, so for an and boolean both sides have to be true for it to evaluate, and left less than equal to right, that's fine on its own, but when you have left is then greater than right, you can see they are contradictory. Both are never going to be true at the same time. Only one side's ever going to be true because they are complements of each other, they're the opposite of each other, so this must be untrue. If you weren't sure though, you could look at the other three, because what it's saying is left is not equal to right. So if left is less than right, clearly they're not equal to. This is, as I say, the complement, and again this is the same idea, that they can't, one of them is going to be true, or either side can be true. Part 4 is the first of the algorithm questions, which people either love or hate, and this is all about, we've basically been given a partial solution for binary search, and we need to really check whether the value has been found or not, because that's the whole point of binary search. So we need to extend the algorithm and introduce a new variable called found, which is true when the value has been found in the array, or false if it hasn't been found. So we need to either write pseudocode or draw the flowchart. I'm going to do pseudocode, that's my preference. It's I find it a lot easier, and I'd recommend doing pseudocode. Pseudocode people worry a little bit about because they see pseudocode looks like this, which looks quite formal, and pseudocode doesn't need to be this formal. The whole point of pseudocode is anyone can read it. You're not going to lose marks for having a different convention to the examiner. So as we saw before, the algorithm ends because left equals right, so left is the same as right in this case, we're both 4, but we're told to use the value of left, so we need to first of all initialize our variable found, and let's set it to false by default, and I'm just following the convention with variables. You could do equal sign, it doesn't actually matter. So found is going to be false just by default. We're assuming the searching algorithm hasn't found our item, we're assuming our item isn't there, and then we want to change it to true if it is. So how are we going to do this? We need to do, let's change colour. So we need to do an if statement first of all, and again I'm going to capitalise it, I'm going to kind of copy AQA's way of doing it. So if our value equals the array and our index, which is left, so 4, then we can change found to true. And we can do end if. And that should be our answer. So let's just talk through what I've just done if I didn't explain it very well. So we basically need to matches when right is the same as left, so 4 is the same as left is the same as right here, which means you've kind of honed in on one value, and we want to check if this algorithm is actually working properly. So we want to match this value against our value we've started with. So basically this is going to be the last value it checks. It's worked down to the 4th index, and we want to check if that value is in fact our target value, which is val. This is the variable there. So we need to basically index our array using the index of 4, because that's what we ended with, and if it matches, then we can set found to true, otherwise we leave it at false. And we could also do something slightly different and ignore this first line and then do else found is false, but it doesn't actually matter which way around you do it. I always like to initialize my variables, so this will get us our 4 marks. And maybe to over-explain, it doesn't actually matter how you write your pseudocode. It could be found equals could be lowercase if, it could be whatever. You could do a semicolon if you wanted to, but this is a nice simple way of doing it, just capitalizing the keywords and keeping things fairly simple. In terms of how you do this with flowchart, I'm not entirely sure. I never really like to do flowcharts, if I'm being honest. I suppose it'd be something like you need to do a big box and basically saying is array left equal val, and then you do one side is going to be true, and then you set found to true, and the other side is going to be false, and you set found to false. So I definitely think pseudocode is more appropriate because it's so simple. It's just 4 lines of code. Question 5 looks to be about sound, so we're going to calculate the file size in bits for a 2-minute sound recording with a sample rate, so sampling frequency of 1000 Hz and a sample resolution of 5 bits. So I think I taught this as sample size and sampling frequency. They're equivalent terms. I'm pretty sure I put a little disclaimer at the end of the video, and we've got to show our working. So the formula for this is file size equals obviously the time times the sampling rate and times the sample resolution, which makes sense. It's not something you really have to remember because we're working out. So sampling rate is how often per second we're taking a sample, and sampling resolution is how much data we're storing per sample. So clearly they're very related and important. And then we're working so this would, on their own, this would be per second, and we need to times it to work out the total amount of time. So we need to make sure we're using standard units. So hertz is the same as 1 over seconds. We need to convert 2 minutes to seconds, so it's going to be 120 seconds. If you plugged in 2, that wouldn't be correct. You need to convert to seconds. This is the base unit of time. So 120 times the sampling rate, that's fine. So times 1000 times 5. This is about as hard as the maths is going to get. You don't have a calculator, obviously. So 1000 times 5 is 5000. And 120 times 5000. So 12 times 5 is 60. So we have to add on 4 zeros. So our answer is 600,000 bits. Part 2 is about converting between bits and kilobytes. So we need to convert units of 24,000 bits. So with a single bit, then we have a byte, which is 8 bits. Then we have a kilobyte, which is the same as 1,000 bytes, so 8,000 bits. And so if we were going from kilobytes to bits, we'd multiply by 8,000. If we're going from bits to kilobytes, we divide by 8,000. So 24,000 divided by 8,000 is easy because 24 divided by 8 is 3 and the zeros cancel, so this is going to be 3 kilobytes. So sound files are clearly stored as bit patterns, like every bit of data in a computer, and they're often compressed. So we need to compress the following bit pattern using run length encoding, and this is a form of lossless compression. So we don't lose any data. We don't want our sound to become, worse sounding. So we need to run length encoding is all about replacing runs of data. So runs are repeats of data, and we want to replace them with what's known as a key value or a frequency value pair. So we write a frequency, then we write the actual value that's repeated. And it doesn't actually matter which way around it is, but we're going to do frequency first. So we have 4 zeros here, that's a run. In fact, we need. So often we write nibbles, 4 bits with gaps in between, but you've got to remember in a computer they're all conjoined, it's just one long bit pattern, so I need to consider the 6 zeros here. So we're going to write 6, and then we're going to write 0. And we could put this in brackets like this, but I'm not going to. but we could do a comma just to split up each pairs. This is just a human readable format. Obviously you'd convert this to binary in a computer. So we then have 4, 5, 6, 7 ones. We have 7, 11, 12 zeros, 12 lots of 0, and then we have 7 lots of 1. So you can see we've got our frequency first and the actual value that's been repeated second. And if we had in a kind of like an isolated value, so if we had like 0, 1, 0, we'd have to write still 1, 0, 1, 1, 1, 0. So you have to do it for single bits of data as well, even if it isn't repeated. And on second thoughts, it's probably better to put it in brackets like this, because you get a bit of confusion when you have double digits. But anyway, that would be our answer. That's the general principle of run-length encoding. Another multiple choice, we've got to show the true statement about run-length encoding. So will it first of all always make the file smaller? Not necessarily. It may make the file the same size if you're very lucky, or it may even make it bigger. So I actually showed the example up here that I've now deleted, where you can actually, if you have single bits of data, it will add, because you're basically adding another value alongside each value. The frequency wasn't there before, wasn't there initially, but you're adding a frequency in. And if you have a long run of data, then it's going to reduce the file size, because you're, it's only a pair of data as opposed to a long length. But if you just have 1, then a 0, then a 1, it'll make it larger actually, because you've got to add the frequencies in for each. So that's not true. It's most effective on data that appears random. Again, that's not true, because if it's random then it's going to fluctuate, it won't have many repeats, so it will not lose any of the original data. By power of deduction that's true, and anyway we would hopefully know that's true because it's a lossless type of compression which never loses data, as opposed to lossy compression. Question 6 is another algorithm question worth 7 marks this time, so it's going to be more involved. And we have the start of an algorithm for converting between 24-hour time to the 12-hour clock. So all we need to do is really convert between the two. And clearly, so we take the input between 0 and 23, that's the 24-hour clock, and we have to actually output the 12-hour equivalent. So we could just do like a case statements where we list every single combination, but it's gonna, I'm sure you'd get a couple of marks for listing every combination, but it's not really what you want to do. You want to find a slightly smarter way of doing it. So we need to basically work out what the relationship is between the 24-hour clock and the 12-hour clock. So straight away, between 1 and 12 in the 24-hour, so let's do 24-hour, 1 and 12 is the same as the 12-hour clock, so it's the same. So 1 AM to 12 PM is the same. Well, actually, no, let's maybe get rid of 12, so if we did 11, that's okay, because 12 will need to actually change, so we've got to also output AM or PM as well. So to transform this into an if statement, really we want to go if the hour is less than 12, we have to just do the hour AM. So actually let's start this, shall we? So, and I'm going to have to rearrange this, I imagine, but if we just start by going if hour is less than 12, then we're going to just output, and let's follow their convention. We could write print, but output hour plus AM. I want to do a space there, but yeah, it's a general idea. So we have to be a little bit careful about doing an else statement here. You might be tempted to go, okay, if the hour is greater than 12, we do this, but we have two exceptions of midnight and midday, which we sort of discussed, which we're going to have to deal with in a little bit. So we can do if the hour is greater than 12, then we want to output. So if it's greater than 12, so if it's like 1 o'clock, the difference between 12-hour time and 24-hour time is we subtract 12, and that's the pattern for this. So we need to do output hour subtract 12 and then plus PM this time. So we've got to write a condition for 12. If it's 12 so far, we're kind of ignoring it. So let's do if hour, well, we could do else here, equals 12, then we want to, so if it's 12, it's going to be midday, so we want to output hour plus PM. So the difference is obviously before 12 it's AM, but after 12 it's, well, including 12 it's PM. Another exception is midnight, as I might have said, because midnight in 24-hour is just 0, but in 12-hour it's 12 AM. So we have to convert between the two, so it's an exception, because if we did, well, 0 is obviously less than 12, so we're going to output 0 AM, which doesn't really make sense in 12-hour time. So we need to do another condition, but we need to change this to exclude it. So first of all, let's just do if the hour is 0, then we want to output just 12 AM, and those apostrophes are very bad, but hopefully you can see what I mean. But we need to actually convert, because at the moment we wouldn't actually ever get executed because it's covered by this so far, so we need to actually add something to this condition to change it. So let's do it in a different colour just so we can see. So we want to basically have an AND operator here, so we could do an actual proper operator, we could just write AND. So if hour is less than 12 and not equal to, so we could just do that, not equal, hang on, let's do this properly. So we want to do hour is not equal to 0, then it should be okay. So not the neatest and not the best design. You could do this with else statements if you did it properly. I try to do it kind of on the fly so you can see my thought process. You're kind of doing it bit by bit, but it should give you this the correct answer from inputting the 24-hour time, even if it's not particularly neat. Moving on, we've got a question about the OR logic gate. We've got to fill in a truth table for this. Very simple, which should be, if you've learnt. So an OR operator or logic gate, basically either side can be true for it to evaluate to true. So if both sides are false, like 0 and 0, it will return false or 0. And if one side is correct, if one side is true, we get an output of 1 representing true, and if you get both sides, then that's true as well. So very simple. It should be, you know, the easiest question of the paper really. We've now got a more complicated logic circuit with 2 AND gates. So an OR gate looks like, it's quite hard to draw, but like a it's curved, it's a bit like a crescent moon, and it's got an output, so 2 inputs and 1 output. This is an AND gate, and this is a NOT gate, so NOT, and this is AND. We haven't got much space here, but we need to do the truth table for each kind of section of this circuit. And if you were to design a truth table yourself, you'd want to kind of take it step by step. If you jumped from A and B to what it outputs right at the end at Z, you might make mistakes, but taking it step by step is a lot better. So first of all, when you have an input of A and B, what does X produce? So when you see this is just a single connection, and often you see this in more complicated circuits, especially as you go on to higher levels. It just means this input is the same going up here. Okay, so A and B, what does it produce? Well, an AND gate is both sides are going to be true to produce it to be true. So both sides are 0 here, so it's going to be 0, and both sides are not equal here, so 1 and 1 is the only way we get 1. Okay, so X is 1 at this point using these different combinations. Then we have X and Y, or we need to work out what Y is. So we have the output of X and the input of B here, so we need to work out what, so we need to look at X and B. So X and B are both 0 here, so AND gates both are going to be 0, and the same here, both sides aren't 1, but at the bottom here both sides are 1, so we get 1 outputted at Y. And now we have an inverter or a NOT gate which just does the opposite, so 0 becomes 1 and 1 becomes 0, and that's our output. A slightly more fun question, we've got to actually do our own logic circuit, and it's for an automatic door system. It has 2 sensors, one on either side of the door, and they are labelled F and B, and it will open when either of these sensors is activated. When you say either, that's a great great keyword for this topic, because that's going to be an OR logic gate. Okay, and we have a switch S which can override this, so it will not open unless S is on, so S has to be on, and the output is whether it's open or not, and that's D. And again, this is the kind of question you'd want to do in pencil probably. So I showed you the, but first of all, when you have either, as we looked at before, OR gives true when either side is true. So in this case, you want to know if one of the sensors is activated, or both. I guess it doesn't matter if it's both. So we want to do an OR gate here, and try and draw it as best I can. Not brilliant. And then we're going to have an output, and it's going to go to D here. And so what happens with S? So in fact, it's not quite going to be quite true. We need to add another gate here, because this is going to be an AND gate eventually here. And I know that because S is kind of the overriding variable here. if this switch is turned off, then the door is not going to open. You need to, turn the door off during the night, perhaps. So we have this switch, and basically we want this switch to have an overriding effect on the output. And so an AND gate, both sides have to be true for it to produce true, and true being the door is allowed to be open. And so the switch needs to be able to produce an output of 0 when it's 0, and so because either side, basically a 0 kills the system, and so if the switch is turned off, then the door won't open regardless of what happens with the sensors. But if one of the sensors or both of them is on and it produces a 1 here and the switch is on, then the door will open. So hopefully that makes sense. You kind of have to be, when you get statements like this, you've got to use the keywords to work out roughly what's going on. Usually there's a few hints, and logically it makes sense. Question 8 begins with 4 separate subroutines that have been written to control the robot: forward, turn left, turn right, and object ahead, which will tell you if there's an object ahead by returning true or false. And so forward is actually moving between what's going to be squares here, and turning left and turning right are just 90 degrees, so they're just this single axis rotation as opposed to actually any movement. And this isn't a question where you would have any theory we've looked at. This is just a purely kind of application question, so they're never going to be too hard. So we've got to draw a path of a robot through the grid below, starting in this square with that direction, using these 4 commands. So first of all, we're starting here, and let's get a colour. So we're going to go forward 2 squares, so 1, 2, and that's horrendously unstraight. Let's do that again. So we're there, and now we need to turn left. So turning left is 90 degrees left, so i.e. we're going that way, and can't really do anything to show that, because I guess a potential mistake is you think turn left is turn left and go forward a square, but we're not doing that. We're just turning the robot so it's now facing in that direction because it's gone 90 degrees left. Okay, now we need to actually move forward 1 square from here, so we're going into here. We're now to turn right, so we're now facing this way, and we're going 1 square, and we're going to end up just facing this way, so you might want to put that there as well, and that would be our 3 marks. Part 2 is a more complicated version of this, so we're given more code here, and we now have objects represented with black squares. So again, we've got to do the path starting from here with that direction using this code. So first of all, we've got a while loop where the object ahead, remember, that returns true if there is an object or false if there isn't, and we're going to loop until here, until there's not an object ahead, basically. So at the moment there is an object ahead, so we're going to enter the loop basically, and we're going to turn left, so we need to visualize it as now going in this direction. And if the object ahead is still true, so there isn't an object ahead here, this is an empty square, we can skip to the end of this if statement and go forward 1, so like that. And now we start again because there is an object ahead here, we're now facing this direction of course, and we want to turn left, so turning left is going to go down, which means we're kind of facing down here, and there is an object ahead, that's true, so we turn right, so we need to now go back facing this way, and now we're going to face this way, so we now need to go forward 1, and now we haven't got an object ahead, so we can skip this whole loop because we're going back to the loop always, and we just go forward 1, and that's the end of the program, and we're facing that direction at the end. So now we need to visit every square in the following grid that does not contain an object. So we need to find a way of going all the way and covering all the distance. And we have to complete the algorithm by writing these instructions exactly once in the correct places of this kind of hollowed out version. So first of all, let's have a look at the instructions we've been given. So we have an initialization of a variable, we have a decrement of a variable, and we have just basic commands for this robot. So first of all, initialization is this one, and that's a clue that, well, not really a clue, it's kind of, I guess, obvious that it's going to be our first statement. We can't use distance -1 without using distance first. Clearly we're referencing itself, so we need to declare it first, or initialize it first, I should say. So distance 4. Then we have a loop, so while distance is greater than 0, and because we have this condition in the loop, we need to use this decrement variable here, so we need to put that at the end just so we know, just so we don't have an infinite loop basically, so we want to put that down here. Now the other 3 are slightly less obvious, I suppose. So we want to cover all the squares, and that means we're starting off here, and we want to firstly just get out of this little hole we're in, so we want to move forward by the distance. So it's probably worth somewhat tracing out what this is going to do. So we have a distance of 4 first, and the distance is greater than 0, so it's going to execute in the first place. So we've got moving forward 4 here, 1, 2, 3, 4, so up here. And now we want to find a way of covering all the distance, so we need to turn left basically, don't we, otherwise we're not going to go anywhere. So we need to do one of these turn lefts, and that's going to kind of give the game away for the other one as well, because that's just the last one. We need to use each one exactly once, as it said. So that's going to be our answer, and let's just maybe trace this out briefly. So it's going to turn left, go forward 1, in fact, go forward 4, so 1, 2, 3, 4, turn left again, so now facing this direction, and the distance becomes less, so it now goes down 3 times, 1, 2, 3, and I think you can probably get a picture. It's going to cover this area just by keep turning and reducing the distance each time, so this makes sense and is correct. For question 9, we're given pseudocode for a famous algorithm that calculates the largest whole number that can be divided into 2 given numbers without leaving a remainder. So the largest common largest common factor, in other words. So if we have 2 numbers, 12 and 16, 4 is the largest whole number that divides into them both. So we need to complete the trace table yet again. We've done this drill before, and our inputs are 15 and 39, and they've done that row for us. So we need to jump straight to the loop. These have been covered, lines 1 and 2. So while number 1 is not equal number 2, well, they're different, so we have to loop. And number 1 is less than number 2, so we go to the else here. So number 2 is number 1 is number 2 is number 2 minus number 1. So that's 39 minus 15, which is 24. They're still different, so we loop again. And now, well, again, number 1 is less than number 2, so we do number 2 minus number 1, so 24 minus 15 is 9. They're still different, so we loop again, and now number 1 is greater than number 2, so number 1 is now number 1 minus number 2, so 15 minus 9 is 6, and it's probably best to do it and leave a gap. Again, the gaps don't matter. They're still different, so we loop again, and number 1 is less than number 2, so we go back to the else, and now number 2 is number 2 minus 1, so 9 minus 6 is 3. And we go again, number 1 is greater than number 2, so number 1 minus number 2 is 3. And now they are the same, so that's it, we're finished. And for 1 mark, we now have to state the line number where selection is first used in this algorithm. So we have 3 constructs, and it's going to ask us about iteration as well. So we have sequence, selection, and iteration. So sequence is where just they're iterated line by line. Selection is where we actually have a condition that we are, one condition is changing the flow of execution. So the first line is 4 here because an if statement is an example of selection, and so it's going to be line 4. And then for iteration is for while loop because we're repeating. An if statement doesn't repeat, it's just a single selection, whereas a while loop will repeat until the conditions are met. So that was line 3 for iteration. And then how many lines use a variable assignment? So we have 2 assignments here, so that's 2, and we have another one here, so that's 3, and another one here, so that's 4 in total. Now we're told that a programmer wants to implement this algorithm in their code, and we have to explain why it would be a benefit to implement this as a subroutine. So a subroutine being this out-of-line block of code we can call loads of times and pass values to. So that's the most obvious benefit, I suppose, that you can reuse it. That's the whole point of a subroutine. You can reuse it as many times as you want without having to, put your code in line loads of times. So it can be reused. And 2 marks, so really we have to state the benefit and then explain it, so 1 mark for each. So this would be a mark out of the way, we have to then explain it. It can be reused because you don't have to write your code out in full each time you call it. So basically you declare your subroutine, it could be in a separate file even in some programming languages, and then in your code you can reference it just in a single line, and then you can have some other code, reference it again and again. So you basically just pass in some data to the subroutine, and this code gets reused as many times as you want. If you didn't have a subroutine, you'd have to write out this code every time you wanted to use it, which is not it's not a good idea. And actually another reason you could put for this is testing. It's very difficult to test if you have so much repeated code. If you have a single instance of your code, you can test and debug this and so on. Also, you might have been taught about interfaces, so you basically have an interface to this because you have the name, whatever it is, lowest common divisor, your inputs A and B, and you can program to an interface. You don't really care about, so you know this will return an integer. You don't really care about what's actually happening in this block of code. Say this is a library and this is someone else's code you're using. You don't really care what's going on. You're just programming to this return value and the input parameters. But that's a little bit more advanced. Maybe probably testing and reusability are the two main reasons for this, and structured programming, I suppose. So you can make your code look a bit nicer as well. We have three variables A, B and C, and they're assigned string values, bitmap, pixel and bit, and we have to shave a logic which shows the concatenation of variables A and B. So concatenation is often represented or overloaded with the operator plus, i.e. add, because really you're adding two strings together and concatenating and you're putting them together. And first of all, space is a character in ASCII. It's got its own character code, so this is not, you can have a string that's just a space, so that's not going to be true. It's going to be bitmap pixel because you're using the values of the strings, not the actual variable names itself. The variable names aren't important to the programming language. It's a value that's assigned to a variable. The variable is just a pointer to some data. The variable names are only really used by us, so programming wouldn't give you A and B, it would give you bitmap pixel, and that's the answer. So strings can also be represented as arrays of characters, a character being a single character and a string being multiple characters. So some languages don't support a string type, they have to use arrays of characters like this. So we've got bitmap, pixel and bit in this array format, and again the indexing is starting at 1, so B is 1 here. And we have to shade two lozenges which correspond to the two true statements about these arrays. Okay, so first of all, let's take this step by step. So the index of A1 is the same as B1, so let's check that first of all. So A1 and B1, they are different, so that's going to be 0. It's going to evaluate to 0. Or A1 is C1, so A1 is, so that's true. So this is going to be true because we're going to get, it's an OR operator, one of the sides is true, so it's going to be true. So this is true straight away, that's 1 down. The length of B is greater than or equal to the length of A, so the length of B is 1, 2, 3, 4, 5, 6, that's A in fact. So the length of A is 6 and the length of B is shorter, so that's not true. I didn't need to actually count that. Next we have not, so you've got to take it in the brackets first and then you can invert it. So the sixth value of A equals the first value of B, so sixth value of A is 1, 2, 3, 4, 5, 6, so that's true. So this little bit would evaluate to 1, and the third value of A is the third value of C, so G, so that is true as well. But crucially we have a not, so we're inverting this. So this would evaluate to, these brackets would evaluate to 1, but we invert them, so this is 0, so that's not going to be true. A equals 5, it doesn't make sense. We haven't got, A is representing the entire array, whereas this is just a single value in the array, so that doesn't make sense straight away unless this is a single value array, and then that is going to mean this is true, but let's check it anyway. So we have square brackets here, so we're indexing, but we want to evaluate this first anyway. So the length of A we said was 6, and the length of C is 3. So this is, so basically we're doing array A3 equals C3. So the third value of A is T, and the third value of C is T as well. So this is going to be true as we worked out. Last question then, worth 9 marks. So as a general rule, you're going to have a 9 marker algorithm question, and usually it's going to be the last question, if not always. So people dread this, but really they're usually not that bad. They can be harder in some papers than others, but make sure, as long as you leave yourself enough time, so maybe you want to leave yourself maybe 15 minutes perhaps, if you can allow yourself that to work on this, then you'll be fine, I think. So we need to develop a subroutine called Prefix using either pseudocode or a flowchart. Again, I'm going to do pseudocode at least first, and we're going to take two character arrays, word and pre, as the parameters, and it's going to determine whether the start of a character array word is the same as all of a character array pre. So we have an example here. So bit is the start of bitmap, so if that was the two parameters, it would return true. If it was B and C, clearly pixel and bit isn't a prefix of pixel, so that's going to return false. So relatively standard, but we've got to be a little bit careful. So it needs to work for character arrays of all lengths greater than 0, so we don't have to worry if it's an empty array. And we have to not assume, so clearly we're going to get a mark for catering to this, not assume that the length of pre is less than the length of word, which is very easy. We just need to do a little comparison to make sure that pre is less than word, is less than the length of word. And it started for us, so we don't have to worry about actually defining the parameters and the name and so on. So first of all, let's just get that check out of the way. So the instructions they give you, often if it's in bullet points, they're going to be really useful, especially if it's in bold as well. That's a clear clue. So we need to just make sure that the length of pre is less than the length of word. So basically if the length, in fact they did that in, let's do it in lowercase, the length of pre. So if the length of pre is greater than the length of our word, then we're just going to return false, because this can't, it doesn't work. This is just a condition that doesn't work. So let's just close this off. So in fact we're going to have else. So we need to iterate over our word array and compare each value with the corresponding one in our pre-array, and if they stop matching, we will return false. So we need to first of all have a counting variable for our while loop to count the indexes. Let's do this in a different colour. So let's do n as our variable. It doesn't actually matter what it's called, usually n or I. I'm going to start at 1. We're going to start the first index because we're assuming it's greater than 0. So we need to do a while, and while n is less than or equal to the length of, it's going to be length of pre actually, because that's the shorter one. So while n is less than or equal to length of pre, so basically we don't want to exceed the index of pre. That would cause an error in a real program. So first of all we need to see if the value at this point, so in word n, so n being the index, equals the same value in pre. If they do, in fact we want to do, if they don't equal, we just return false, because that means they don't match straight away. And things like the indenting you don't need to do, but I'd recommend, it makes it look a bit better. And then we need to just end if, and really importantly we need to increase the value of n, so n could do plus equals 1, just to increase n, because otherwise again we're going to get trapped in basically an infinite loop. So what we're doing here, we have got our two arrays and we're looping over pre, so the index being represented by n, and we're increasing n each time, and if this value doesn't match, then we're getting rid of it. If they do match, we're looking at the next one, and basically we're needing to make sure that all the values in pre are matched by the first values in word. So basically this is all we need for our while loop, so we can kind of close our while loop off here, because if it's got through this while loop unscathed, if it hasn't returned false at some point, then that means the whole of pre must match the start of word, so we can return true at this point. And I don't know how well aligned this is, but end if, and we can even do end subroutine as well. So that's basically our code. Not very complicated really, and it's worth it's worth 9 marks, which is quite a lot. So I think anyone would be able to program this in a programming language. It's just obviously in exam conditions it's a little bit more stressful, which is why you've got to make sure you leave yourself time. I've known some people to go and do this question first. They skip to the end to do this question first. I never did that personally. I would rather kind of build up to it. I'm not always at my sharpest at the start of an exam. So you need to kind of work out what you're going to do going into it. To overemphasize, you've got to make sure you don't ever go outside your index range, otherwise you get an out of bounds error. If you went beyond the length of this, you would hit an error because you would trying to access an element that doesn't exist. And if you were zero indexing, if n starts at 0, you've got to do length pre minus 1, but we're starting at 1 in this example. And again, really important you increase your variable that is used in the while condition, otherwise you'll have an infinite loop, which is never going to return true in that case. Anyway, I hope this video was useful. Let me know if you have any questions or feedback, or if it helped, and I hope the exam goes really well.